So I'm just waiting for a couple of students to join. Today's class will be the last class on module number 3. So from next class, that's on Monday, I will begin module number 4, which is about forced convection. So it's quite a big module, and also you will be introduced to certain new type of solutions for heat transfer problems, especially the convection problems. So uh, try not to miss classes on convection. In fact, every class is important because every class you get to learn more. Okay, so in today's class, as I have told you the previous class, I will take up a, a new way of solving heat conduction problem, especially the two-dimensional problem. But doesn't mean that whatever you are seeing today is restricted to two-dimensional problems. It is also applicable for one-dimensional problem and also three-dimensional problem, and also steady state as well as a transient. So it's a very general way of solving problems, and it's a beautiful technique based on mathematics, and therefore its wide usage is possible because of the availability of high speed computers. So that's what we are going to see in today's class. So without further ado, let me share my slides. All right. So this was the one of the first slides that I have shown you when I started this particular module. So solution methods for two-dimensional heat transfer. So this, when I say two-dimensional, it's a two-dimensional steady state, it's a two-dimensional unsteady state with heat generation, without heat generation. So this phrase, two-dimensional heat transfer, is a general one, applicable for everything. So what are the solutions available? The first one is the analytical solutions. We have seen that there are some derivations possible. The equations looked a little bit complicated, but they give accurate solutions, but their application is limited. Only simple problems can be solved analytically. These analytical solutions also are also called as the closed form solutions. Okay, so these are based on mathematics, the solutions of the ordinary differential equations or the partial differential equations, which are based on calculus. The next one is the graphical solutions. We have seen this conduction shape factor, and we also seen that these graphical solutions are possible when the boundary conditions are either a given temperature or given heat flux. No, insulation boundary condition, temperature and insulation boundary condition. Okay, these two conditions. The last one is what we are going to take up, the numerical solutions. So any problem can be solved, and accuracy depends on the fineness of the grid. So you can see any problem can be solved. So this particular numerical solutions depend solely on the 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 computers computational power, or the processing power, or the computer's ability to handle a large number of unknowns. So we will see that method now. So earlier we have seen this analytical solutions, then graphical solution. We have also solved some problems on these graphical solutions. Conduction shape factors, we have seen this. We also solved some problems. Okay. Then coming to the numerical solution. So this is today's topic. So analytical solutions may be obtained only in a few cases. What cases? Where the calculus is available for us to solve. So that can be limited. You may not be able to apply this methods of analytical solutions to solve a problem that may arise in future. There is no guarantee. It depends on how simple that problem is. So solution is not guaranteed by analytical methods, and only limited cases can be solved. In most practical cases, such solutions are not possible. So, because in most cases, what happens is the geometry of the object that we are considering may be quite complex, and that may not be fitting into one of these uh, three coordinate systems that we have seen: Cartesian, cylindrical, and spherical coordinates. So, in such a case, we may have to go for a, a, a another system in which you can describe the geometry, which may not be amenable for analytical solution. So this is due to the complex geometries. So why this analytical solution limitations is because of the complex geometries and also the complex boundary conditions. So if analytical solutions are not possible, and if this two-dimensional graphical solutions is not possible, then what we have is the numerical techniques. Numerical techniques can be used to solve any problem. Can be one-dimensional problem, two-dimensional problem, three-dimensional problem, 1D transient, 2D transient, 3D transient, or steady state also. So moreover, numerical methods can be readily extended to three-dimensional problems. So you see, all dimensions, and also the fourth dimension, the time is called as the fourth dimension. So the transient conditions also can be implemented. In contrast to analytical solutions, numerical solutions enable determination of temperature only at a discrete point. So this is one important uh, thing you should keep in mind. This numerical solutions that you are going to see, they give results at discrete points, whereas the analytical solutions give you results at continuous points. Okay, what is this discrete? What is this continuous? You'll understand later on in this class. Now, the basis of this numerical methods of solution is the Taylor series expansion. So from calculus, from mathematics, you know that this is the Taylor series expansion. It's an infinite summation series. The function of x plus delta x is equal to function of x plus delta x multiplied by dfx by dx plus delta x square multiplied by d square fx by dx square, and so on and so forth. What happens is, since when we deal with very small delta x is the discretization size. So when the delta x is very small, the delta x square is even smaller, and the subsequent terms, the delta x cube, so on and so forth, they are extremely small. Therefore, as an approximation, we ignore the third term and further. So ignoring third term and beyond, third, fourth, fifth, it's an infinite summation series. So from the third term onwards, we ignore, because the amount contributed by the subsequent terms is extremely small. So ignoring the third term and beyond, we try to, so if we ignore the third term, what happens? This one we are ignoring. So what remains is this one, and this term. So from these three terms, I will try to isolate this one, dfx by dx. So you see dfx by dx is equal to f of x plus delta x minus f of x divided by delta x. So that's what is there. So you see this derivative of a function with respect to a independent variable is written in terms of you see this is a calculus notation, but this is an algebraic equation. So this differential or this derivative is now written in terms of an algebraic equation. Okay. Now, where do we apply this? Here. See, you see there is a plane wall. There is a one-dimensional heat transfer taking place, because of which there is a temperature distribution along this. You see this blue line. This is the temperature distribution as a function of the distance x, as a function of x. X is in the horizontal direction. See, this is a one-dimensional temperature distribution. We are not come into two dimensions. So in this one-dimensional temperature distribution at different points, you see, we start breaking up this 0 to this point into some m number of points. So we'll number them also 0, 1, 2, and so on. And at some point we have m minus 1, and we have m plus 1. Just like on the either side of 1 we have 0, we have 2. On either side of 2 we have 1, and here we have 3. Okay. So we have taken point m. Before m there is a point m minus 1. After m there is a point m plus 1. So if we apply what we have seen here to the temperature, in place of fx I write t. So temperature, fx is a function of x. Likewise, temperature is a function of x. So for this temperature distribution, if I implement this notation, dt by dx at m minus 1, m minus half, See, this is point m minus half. This is the point which is m plus half. So m at m minus half, this can be written as a tm minus tm minus 1 by delta x. At this point, Tm minus Tm minus 1 divided by delta x. What is delta x? This distance is delta x.
Sir,
Okay.
how the Tm and Tm minus 1 is coming, sir? I didn't understand.
See, this is Tm. The temperature distribution is available along the length, along this length, along the x-axis. So we chose point M minus 1 and point M plus 1. Okay. Point M is here. Point M minus 1, temperature is this one. Point M plus 1, the temperature is this one. So this thermal gradient, you see at this point, if I want the thermal gradient, what I do, this value minus this value, it's like this thermal gradient, this value minus this value divided by delta x. So that is what is done here. You see dt by dx, this is nothing but the gradient, isn't it? This is the slope.
Yes.
You also know, but the derivation of the slope we have shown here from the calculus using the Taylor series expansion. So dt by dx at m minus half is Tm minus Tm minus 1 by delta x. The Tm means temperature at point M. Tm minus 1 is temperature at point M minus 1 divided by delta x. Similarly, dt by dx at m plus half. See, this is m plus half. This is m plus half. At m plus half is Tm plus 1 minus Tm divided by delta x. Okay. And now we'll go a little bit further. What is d square t by dx square? D square t by dx square is a derivative of dt by dx. Okay, d square t by dx square is equal to d by dx of dt by dx. Okay, so if I want to find the d square t by dx square at certain point, m plus half at m, let us say, then we have the dt by dx at point ahead and dt by dx at point behind. At m plus 1 by 2, we have dt by dx, and at m minus 1 by 2, dt by dx divided by delta x. Okay, so using this as the basis, we will write this once again. Now, dt by dx at m plus half is available for us here. So this one. And dt by dx at m minus half is available here. So this minus this divided by delta x. So if you simplify this, it will become d square t by dx square is Tm plus 1 minus 2Tm minus Tm minus 1 by delta x square. So this is d square t by dx square at m. Okay. So the second derivative can be written in terms of the temperatures in this manner. So first derivative could be written in terms of this, like this. So what we are doing here basically is replacing the derivatives with the variables, I mean dependent variable and the independent variable. So we are converting the differentials into algebraic equations. So you see d square t by dx square is written in terms of temperature at Tm plus 1, at Tm plus 1, temperature at Tm minus 1, and temperature at Tm. Okay, so you take this slope. This is basically the slope. T temperature at this point divided by temperature minus temperature at this point minus 2 times the temperature of this point divided by delta x square. That gives the second derivative of temperature with respect to x. Now, why we are folks? Why we are trying to come to d square t by dx square? Remember the equation. The original equation for two-dimensional heat conduction is d square t by dx square, or dou square t by dou square t by dou x square plus dou square t by dou y square is equal to 0. This is two-dimensional heat conduction without heat generation and constant properties and steady state. In this, d square t by dx square can be written like this. Similarly, if you rewrite this in terms of y, d square dou square t by dou y square can also be written in a similar manner. So that's why we are trying to do. Now let us extend what we have seen. See, what we have seen now is for 1D. only x is involved. That's why we wrote it as a dt by dx, because only one independent variable x. Now let us extend this to two dimensions. That's all is called as a nodal network. So you see there is a domain. This domain is like a graph paper. You see, it's a graph paper. If you want to find out the area, what will you do in this domain? If you want to find the area, you learned this from high school or plus two. You will count the number of squares. You know, one square is 1 square centimeter area. So you count the number of squares and multiply with the 1 square centimeter. You will get the area available. Well, basically, what you are doing is integrating to find the area. So likewise, we'll try to extend what we have seen for two dimensions. So we'll take one point here. This point we will take, and it is exaggerated here. The center point and the crosshairs is named as a m, comma n. M in the x direction, n in the y direction. So in the x direction, if you move to the next node, this is m, comma n is called as the central node. And on the right side, you get m plus 1 n. That means this one is m plus 1 n. And this one is m minus 1 n. Similarly, if you go upwards, it will be m n plus 1. So this point is m n plus 1, and this point is m n minus 1. So you can see here this temperature distribution is given in terms of these different points m minus 1, m, and m plus 1. So if you want to write dou t by dou x at m minus half and n, m minus half, m minus 1 by 2, this one, and n. So at this point, if you want to write the dou t by dou x, it will be the temperature before that minus the temperature after that divided by this delta x, this distance. Okay. Similarly, dou t by dou x at m plus half n. That means at this point, it will be temperature ahead minus temperature at the back divided by delta x. So if you want to evaluate the derivative at this point, the temperatures that are involved are this one, this one. If you want to evaluate the derivative at this point, the temperatures involved are this one and this one. Similarly, if you want to evaluate the derivative at this point, the temperatures involved will be this one and this. Similarly, at this point, temperature will be this one and this one. So this is called as some kind of a finite difference. You are transforming the derivatives to some difference equations. So you see this negative sign is coming. That's why it is called as the difference equations, finite difference equations. Why finite? Because this delta x is a finite number, finite value. What is delta x? This distance is delta x. Now, if you want more accuracy, you break this into much finer squares, much smaller squares. Then the delta x will be much smaller, and you'll get better accuracy. But then you will see there are some other problems coming up. So what we have seen till now is we have extended the concepts to a two-dimensional thing, and you can see dou t by dou x is written like this at different locations. Dou t by dou x and dou t by dou x at m plus half n is written in terms of temperatures and delta x. Now let us extend this to the heat conduction equation. The heat equation in 2D with no storage, no generation, and constant thermal conductivity is this. Dou square t by dou square, dou square t by dou square is equal to 0. To obtain a numerical solution, the above differential equation must be approximated using a finite difference form. So we should replace this partial derivatives with some algebraic equations. So we have seen this algebraic equation here. D square t by dx square is written like this in terms of temperatures and the discretization size. Likewise, here also, if we can replace this with such an equation and this with such an equation, we will get one algebraic equation. So you see here how to write dou square t by dou x square. Dou square t by dou x square at point mn. At point mn is dou by dou x of dou t by dou x, and dou by dou x of dou t by dou x. Dou t by dou x is dou t by dou x m plus half n minus dou t by dou x of m minus half n divided by delta x. So if you rewrite dou t by dou x as a t m plus 1 n minus t mn by delta x, which we have seen earlier, And similarly, this term in terms of this and substitute in this equation, you will have dou square t by dou x square is t m plus 1 n plus t m minus 1 n minus 2 t m n divided by delta x square. This is for dou square t by dou x square. So all the derivatives are in the horizontal direction. Now, if you extend it to the y direction, dou square t by dou x square will also be like this. In this, the second derivative of temperature with respect to y will be t m n plus 1, m n plus 1, t m n minus 1, and t m n. So t m plus 1 is m n plus 1 is this, t m n minus 1 is this, and t m n is this. So you see, partial derivatives have been transformed to algebraic equations. Now we substitute them in this original equation. So the approximate value of this one is this, and approximate value of this one is this. Why I'm saying approximate is because you see, we got these equations by terminating the Taylor series expansion. So we are having some termination error. That's why we are calling it as approximate. Now, in a special case, if delta x is equal to delta y, that means if we are dealing with a square object and we deliberately keep delta x is equal to delta y, certain simplifications will take place. So then the denominators will be equal. You can add the numerators and take the denominators to the other side, becomes 0. What happens is you will have only a few terms left. You have tm plus 1 n, tm plus 1 n, tm minus 1 n, tm minus 1 n, tm n plus 1, tm n plus 1, tm n minus 1, tm n minus 1, and you see minus 2 tmn and minus 2 tmn. These two together will be minus 4 tmn. Now I am interested in finding out this temperature tmn. So I isolate this one. So I will take it to the other side, right, and bring 4 to the denominator. So tmn is equal to this entire thing divided by 4. So this is what you get. Now you see here, it gives some physical sense. What it means is temperature at the center point is the average of this temperature, this temperature, this temperature, and this temperature. So basically, to find this temperature, you add these 4 temperatures and divide it by 4. That is the meaning. Okay, so this is the way in which we can reduce the partial differential equations to algebraic equations and come up with a system of equations. Now remember, this one is one point in the entire domain. This was the domain. Yeah? This was the domain. I chose one point here and wrote this differential equation, wrote this difference equations. Similarly, how many points are there? There are so many points. If there are 100 points, I will have if there are 100 points, I will have 100 nodes, and 100 nodes means 100 temperatures and such. So 100 such equations. Now solving 100 such equations is a Herculean task. Manually, it's very, very difficult. So, but there are ways of doing it. Mathematically speaking, if, let us say you have not 100 but 5 or 10 equations. What you do is you can use matrix inverse method to solve them, or Gauss-Seidel iterative method to solve them, and so on and so forth. There are a lot of methods. But imagine having 100 equations, 1,000 equations, 10,000, 1 million equations. Then manually it's impossible to solve. That is where we bring in the computer. Programming this kind of equations and solving them using a computer is easier. So see what we have done here. We have transformed the partial differential equations to algebraic equations. The original equation looked like this. The current equation is looking like this. We are more comfortable at solving this equation rather than this equation. But then now you understand what's the problem with this equation. We have such equations as many as the number of nodes. So more number of nodes, more equations. So the solving becomes Herculean, and you will need a high-speed computer to solve. Okay, this is the concept that I want to drive in. Okay, so what the example that I have given you is for the case of a two-dimensional steady state heat conduction. Now, this equation is available in page number 63 of your data book. Page number 63 in your data book, check that. You have that the first equation for the interior node. See, this is the interior node, and for the interior node, the temperature of the central node is basically the average of all the four surrounding nodes. Now, what do we do if there is a convection? Let us say there is an object, and at the surface there is a convection. For that also, there are ways you will have to work similarly and come up with this kind of an equation and then implement it in the solution procedure. So how does the equation look like? That is given in the second equation in the same page 63 of your data book. If you have a convection boundary at, let us say, on this surface, right side surface, you have a convection boundary, what to do? Okay, so in that case, you see here, there is a equation which you have to use. The next equation is exterior corner with convection boundary condition. So in some cases, what you have is there will be convection at this corner, at this corner, or this corner. At this corner, if you have convection, what to do? So in such a case, there is another equation given here. So anyway, the first equation only, as for your undergraduate course, we will focus on the first equation only, and we will take up the first equation only. Other things are a little bit tedious, complicated, and anyway, manually the solution is extremely difficult. So we'll skip that. Only for your understanding, I'm saying that there are different kind of this equation for different boundary conditions. So if you have a convective boundary condition, you will have a different form of equation at the boundary. See, interior node is still the same. Interior node, when we say interior node, this one. Interior node, this is this. For the temperature of this is average of these four temperatures. But what will you do when you come to the boundary? At the boundary, you will have to implement the boundary conditions. The boundary condition can be constant temperature or a given temperature. One example we'll do now. And other possible boundary conditions are convective boundary condition and heat flux boundary condition, and also sometimes radiation boundary condition. If you have radiation boundary condition, then you see radiation, the temperature is raised to the power 4, and then things become non-linear. And the raised to the power 4 means is a highly non-linear, and solving non-linear equation again is a different ball game altogether. Okay, so because of that, so solving equations becomes a big deal in this numerical methods, and solving multiple equations, hundreds, thousands, sometimes millions of equations simultaneously. It's a huge task. For that only we need high-speed computers. And these computations sometimes can even take a few months to run if the domain is large and the mesh is fine. Now, to demonstrate what we have seen till now, I will explain to you a problem. Now, the similar kind of a problem is given to you as an assignment. So, I uploaded the digital assignment for you. So, if you follow this example that I'm going to work out, you will also be able to follow and do and solve the assignment. So the question is, determine the temperature distribution in the plate shown below. So there are two images you see here. The left side is the question, and the right side is the answer. So left side is the question. Unknown temperatures are there. So here we have a plate where the four sides of the plate are at four different temperatures. Left side is at 75 degrees Celsius. Right side top is 100. Right side is at 50, and bottom is at 0 degrees Celsius. We are asked to find out the temperatures of these 2 points. How many points are there? There are 9 points. When there are 9 points, we will have 9 unknowns. 9 unknowns means 9 equations. That means it's becoming a solution of simultaneous equation. Fortunately, they will be linear. And after solution, you should be getting these answers. Okay, these are the answers. This is the temperature distribution. So how to solve this problem? So this is the This is the question. How to solve this? I will show you now. Okay. Now I will frame the equations first. Okay. I will just mark these points for our understanding sake. I will call one. This is T1, T2, T3, T4, T5, T6, 7, 8, T9. Okay. Now I will frame the equation so that I can solve them. Now you see here T1 from the formulation that what we have seen is for an interior node, this is an interior node. Boundary node will be somewhere on the boundary. Okay, but for the boundary, fortunately in this problem, the temperature is given, so we don't have to determine the temperature. So for the interior node, the concept says that the temperature T1 is basically average of the 4 surrounding temperatures. What are the 4 surrounding temperatures? One temperature on the left, one on the top, one on the right, and one on the bottom. So T1, I'll write T1 is equal to 75 plus 100 plus T2 plus T4 by 4. As of now, T2 and T4 are not known, so we'll need more equations. So now I'm writing the equation for T2. T2 is equal to 1 plus 100 plus T3 plus T5 divided by 4. You see here, when I am interested in point 2, I am taking the 4 surrounding them. So T1, 100, T3, T5. Similarly, if I want to write for T3, then T2, 100, 50, and T6. That will come. So T is equal to plus 100 plus 50 plus T6 divided by 4. Okay, the above equation also divided by 4. Okay. Now further, T4 is equal to 75 plus T5 plus T7. T4. 75 T1, T5, T7 by 4. Then T5 is equal to plus T2 plus T6 plus T8 by 4. And T6 is equal to 5 plus T3 plus 50 plus T9 divided by 4. T7 is equal to, for T7, the left hand one is 75 degrees Celsius. So 25 plus T8 plus 0. And E8 is equal to 1 plus T5 plus T9 plus 0 divided by 4. Then T9 equal to 8 plus T6 plus 50 plus 0 divided by 4. Here I have I have 9 unknowns, and therefore I have 9 equations. I have framed these 9 equations. Now the process is to solve these 9 equations. 9 equations, 9 unknowns. This is mathematically solvable. Now imagine if you have 100 points, you will have 100 equations, 100 unknowns, therefore 100 equations. It becomes a little more difficult to solve. Now how to solve these? I will demonstrate it using the interactive heat transfer software. I hope all of you have
Yes, sir.
installed it in your computer. Did you?
Yes, sir. But so I have a doubt over here.
Okay.
Why are we taking T5 equal to T4 plus T2 plus T8 plus T2? Why can't we directly take it as 75 plus 50 plus 100 plus 0? Because
T5. Huh?
yes, sir.
T5. No, we have discretized it. So it's we are interested. We will see the immediate nodes will have more influence than the far away temperatures.
So T5 anyway has to lie in the center of the plate, so it can be taken as 75 plus 50 plus 100 plus 0 by 4.
What's the value? Evaluate and see 75 plus 75 plus 100, 175 plus 50 is 225. No, 225 by 4.
56.25.
How much?
56.25.
56. Yeah, see, you're close to that. So this is supposed to be 56.11. So you're close to that. Fine. But
So because there is a
see,
method called
it doesn't
Leibniz
have
iteration process.
what?
Leibniz iteration process. There was a method in numerical analysis.
Okay, but what will you do with T2?
So
See,
in this
for
for
T5,
T2,
you're avoiding one equation.
yes, sir.
What about other things? There are 8 other unknowns, no?
Yes, sir. But for T2, we can take 100 T5, and in this case, 50 and 75 would do, I think.
No, it won't work like that. You try that, but anyway, so that will be over simplification. Okay. So the influence on this node will be more of the immediate surrounding nodes rather than the far away temperatures. Okay, so that is how it will work. Now, I'm transferring these equations to the software interactive heat transfer. Now let me share. I may have problems in sharing this interactive heat transfer like we had it last time. Are you able to see my interactive heat transfer software screen?
No, sir.
No, sir.
No? Okay. I think last time
So
we
I
had
think we
similar
have said
problem.
share the full desktop.
Okay. Okay, fine. I will have to do that then. Okay. How about now?
Yes, sir.
Okay. Now I have written some equations in the PowerPoint. And now I copied them and pasting them here. Okay. Now, how I have written them, I just wrote like we do on a paper using a pen. And if we have to continue solving using paper and pen, then we will have to take each equation and eliminate some terms and use some algebra, some mathematics knowledge and do that. But this software does it like this. I will see I have typed these equations like I write with hand and I press on the solve button. And you see it one window pops up saying that these are the initial guess values. Basically, it takes 1 as the initial guess value. So this software works on the iterative process. It assumes some value initially, but updates those values until the correct values are achieved. So this is the initial guess values. I will say OK. Once I say OK, you have the solved solution here. You see here, these temperatures have been obtained right away. So after solving all these 9 equations, these are the 9 temperatures that have been obtained. Okay, so this is one way of doing it.
Sir, it's giving 56.25 as T5.
Okay, fine. So it works in this case because the discretization is coarse, not fine. Okay, but I advise you better not do that. This case is extremely simple, but for complex cases, you may not have the same thing because some other influences will come up. Okay. Now I'll show you another way of doing this problem. I will use Excel to solve this problem. I will open a sheet And in this, you open one Excel sheet and then go to File, Options, and in the formulas, you have to enable, you have to tick this box, enable iterative calculations. Basically, by default, it will be unchecked. You will have to check it and then say, okay. Okay, now I will try to build this plate here. A square plate. So 1, 2, 3. Okay, now I'll make its background. Okay, now what we are given is the surface temperatures in the problem. What we have is left side 75, right side 100. So this is 100. These are 0. Okay, this is what is given, and we are asked to find out these temperatures. So what you have to do is first you have to corner node. You see this corner node. We will have to write something for the corner node. The simplest way of dealing with the corner node is to take it as an average of these two temperatures. Okay. So because you see the top surface is at 100, side surface is 75. The corner one will be an average between 100 and 75. So this is and here also this corner node also. All the corner nodes are known. Now we have to find out these values. So this temperature is basically an average of this, this, and this. Okay. So I will say is equal to this plus this plus this plus this. Now I'll copy this formula in the entire domain where the temperatures are not known. So now you see here we have these are the calculations done. Now remember these are iteratively calculated. Okay. So this is the temperature distribution. So it's we have basically solved 9 equations, but in a fraction of a second the software has solved. Now, if you want to plot a contour plot of these temperatures, then you go to insert, use this contour plot or something like this one or this one. So this is the contour plot, and in this contour plot, 5 levels are drawn. But in the temperature range 0 to 20, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. So 5 levels are drawn. So this is how you need to solve this kind of problems. Now I will now show you your assignment. Your assignment, there is a square plate, and the 4 sides of this square plate are subjected to 4 different temperatures. So left side is T1, top is T2, right is T3, and bottom is T4. Now, there is also a table of values. So each one of you have a different temperature. So first person 17 VME 1064, for that person T1 is 278, T2 is 331, T3 is 490, T4 is 1358. So these numbers were obtained randomly using a random function in Excel. So I want you to use these temperatures and find temperature distribution in this domain. Okay, like the procedure I have shown. So these are the instructions. A square plate has its 4 sides at temperature shown. The left face and all these faces are at these temperatures. Each student is assigned a different set of temperatures as shown in the table below. Evaluate the temperature distribution in the plate at 25 different points. So the example I worked out, there are only 9 points. Here there are 25 different points, and then manually, not using a software, manually plot 5 contours at 5 different temperatures covering the entire range. For example, the range of the temperature that you have, for example, let us see for the first person, the range, the minimum is 278, maximum is 1358. So choose 5 different temperatures. For example, the first temperature can be 300 degrees Celsius. Second one can be 500. Third one can be 700. Fourth one can be 900. Fifth one can be 1100. So in this range, in this minimum to maximum, choose 5 different temperatures and plot the contours manually. That is important. I want you to plot these contours manually and show all the steps and solution procedure in detail. So I want you to write down the equations. Solutions, you rely on software. You obtain the solutions using software, and finally show the solutions. So you will have to draw the domain, mention all the temperatures in this, and in the next drawing you should show the contour plots. That means in your answer I need to see 2 figures. One is this plate with all the temperatures marked, with all the unknown temperatures marked after solving, and then the contours also. Okay, so that is going to be your assignment, and I have given till 25th time till 25th March. So you have more than 20 days time. So just before CAT, you can finish it. Okay, it's very simple if you rely on software, but contour plotting can be done, and manual contour plotting, if you don't know, there are videos in YouTube which you can which you can refer to and plot them. Okay, I will be checking your solutions using I have already developed one Excel chart for this assignment. So for each one of you, I will feed the temperatures given to you, and I will obtain the uh, temperature values as well as the contours. Okay, in that way, I will be evaluating your answers. Okay, if you have any questions, you can ask. All right. So there are no questions. Let me stop the recording here. I'll take your attendance.